Hello everyone. So in the last episode, I talked about the concept of topology, topological space, and open sets. And in this episode, I will talk about the concept of basis and sub-basis. So at first, let's look at the definition of basis. After this, I will talk about why we need the concept of basis and why it's useful. So first, the definition says that if X is a set, a basis for a topology on X is a collection B of subsets of X called basis elements, such that they satisfy those two properties. So we can say a basis on a set X is actually a collection called B, and the elements of the collection are the subsets of X, and those elements are also called the basis elements. And the basis elements satisfy the two properties like those. We can say that the definition of the basis and the definition of the topology in last episode are very similar. And both of them are the collection of subsets of X. But the difference is that the elements of the basis satisfy those two properties, but for the topology, they satisfy other three properties. Okay, so let's look at the properties that the basis elements should be satisfied now. The first property is that for each element X in the set big X, there is at least one basis element B containing X. So it means that if we have the set X looks like this, and we have the collection B like this. So this is X, the set X, this is the collection B. Then for any element of the X, we call it X. For any element, we can find at least one basis element B from this collection, the B here. And this B should be a subset of the X not containing this point X. So this B should contain this point of X like this. So like this. So if we can, like for any point X, we can do this thing. We can always find a basis element inside this collection to contain the point. Then the first property is satisfied. Like for example, there is another point Y here. We can find another basis element by. Let's call it by. And this by contains the Y in the X like this. So this is the first property. And the second property is that if X belongs to the intersection of two basis elements, B1 and B2, then there is a basis element B3 containing X such that B3 is contained by the intersection of B1 and B2. And this means that if we have two basis elements, B1 and B2, B1, B2 like this, when we put when they are in the set X, they look like this, B1 and B2, and B2 like this, and they have if they have intersection area like this, this area is the intersection of those two subsets, and for every element inside this area, like this. We call it X, or in order to differentiate it with from this X, we call it X1. So for any element X1 inside this area, we can find another basis element B3 in here, in this collection B3. The B3 contains this point X, and this can be easily satisfied because of the first property. But in addition, this B3 should be contained inside this intersection B1 and B2. So we should not only find a B3 to contain this X, but we should also require this B3 to be inside this intersection area. So it should not go outside the intersection area like this. This is invalid. So for this one it's valid. So this is B3. If for every element inside this area we can do this thing, then the second property is satisfied. So if this collection B, the elements of the collection B satisfies all the two properties here, then this collection B is called the basis of the X. So that's the definition of the basis. But why do we need this concept? Why do we need the basis? The reason is that because in the topology, because the topology is very important, because we can see that according to the name, right? The topology is very important, and sometimes for a set, it is not very easy to find the topology for this set X, but it might be easier to find the basis of the topology in this set X. So for some problems, we may not be able to directly find the topology of the set X, but we can build the basis at first. Then we can use this basis to create or to generate the topology. So that means if we cannot directly get the topology, then we can use to build the basis at first, then use the basis to build the topology. That's why the basis is very useful. And in the later discussion, we will find that the topology, the basis B, is actually a subset of the topology. So the topology may look like this. The B is a subset of the T. So this is also why the basis B is easier to build in many situations, because it's just a part of the entire topology, and so the subset B may have less requirement as the topology T. So that's why B is easier to build. Okay, so now let's look at how can we use a basis B to generate the topology T. So here describes how we can use the basis B to generate the topology T, and we call this this topology T, we call it the topology T generated by B. So the way to do this is that at first, because the topology T is a collection of the subsets of the set X, so the elements, we call it T1, and and any element in this collection T is actually a subset of the set X. So this T1 should be a subset of the X. So according to the definition of the topology, in order to have one subset, we call it A, to be a element of T, we should satisfy those three properties we talked about in the last episode. But there is another way we can define the topology without verify if all the elements satisfies those three properties. Another way is that because the topology, the elements of the topology are the open sets of the set X, as we talked in the last episode. So if this topology can include all the open sets of this set X, then this collection is called a topology. So that is another way we can define the topology. We just include all the open sets. But how can we do that? How can we, because we have a lot of subsets A, B, C inside this set X, the other subsets. How can we decide which subset is open and we can put inside this collection and make it as a topology? And the method is that we can use the basis B. This basis can be judged. It can determine which subset of the set X is open set. And for example, if we have the subset A here, then this basis B will judge if this A is an open set or it is not open. If it is open, then we can put it in this T, collection T, like this. For another set, for example B, we use this basis B to determine if it is open or not open. Then we find, according to the basis B, we find that B is not open. Then we will not put B inside this collection T. Then after we use the basis to determine to judge all the subsets inside the set X, then we can know which are the open sets, which are not open sets. Then those open sets we put in this collection T, and this collection T will be a topology. So that's the process and the idea to build the topology T based on this basis. So this is the idea, the top level, higher level idea about this process. But how can we do that? How can we use this basis to judge if a set is open or not? Then here it says, it describes how we can do that. So the process is like that. For a set, subset U of X, maybe here we have a U like this. U is a subset of this X, and if it is said to be open in X, it should satisfy those properties like that. For each X in this U, let's put this U at here first. This is a U. For for any x inside this U, there is a basis element B inside the collection B, the B at here, such as the x is inside this B, contained in this B, and the B is contained in this U. So let's change the color. So for any x inside of this U, we can find a basis element in the basis that such that the basis element B contains this point x, and also this B is inside this U. So it looks like this, but if the basis element looks like this, or looks like this, or looks like this, those are not valid basis elements. Only like this is right. So if we, for any element inside this U, for example, there is another point called x1, we can find another point, another basis element B2, B1. It contains x, and B1 is inside this U, like this. Then for any point inside this U, we can do this. Then we can say this U is open, and then we can put it inside this collection T. So that is how can we determine if a subset of the X is open set or not, and that's also the process. How can we build the topology to generate the topology according to this basis? So this process is very interesting, and it's actually the definition of the basis elements are very similar to the definition of open balls in Euclidean space. Because in Euclidean space, if U is a open set, for any element inside the U, it will have an open ball to contain it, and the open ball should be inside this U. So the basis element is just like a generalization of the concept of open balls in Euclidean space. Okay. There is one more thing, that is this sentence says that each basis element is itself an element of T. This means that for all the elements and all the basis elements inside the basis, they are elements of the topology T. So for example, because B1 is an element of the basis, so B1 should be an element of the topology T as well. And similarly, this if we have B2 is a basis element, then the B2 should be an element of the topology. So so this is the meaning behind this sentence. But why this is true? Because for any basis element in the basis, according to the definition, they should be subset of X. So, for example, for B1, it should be a subset of X. And now we can say because B1 is a subset of X, and it is also inside the topology T, then it means that B1 should be an open set of the X. So B1 is open in this topological space X. So, but how can we prove that? How can we prove B1 is open? Now we can use the process we used before. We use basis B to determine the subsets of X if they are open or not. So we can also use the basis B to determine if B1 is open or not. So we can put B1 at here, B1. Then we use basis B to determine if B1 is open or not. So what should we do is like before, for any element X inside this B1, like here for any X inside this B1, we should find a basis element inside this B. We should find a basis element from B, and this B should satisfy two properties. One, the B contains the point X, and two, the B is contained in the U, or here the U is B1. So those are the two requirements for this basis element B. So how can we find this B inside of this basis? If we can find this B, then this B1 is open set. The answer is, of course, we can find the B in the basis, and this B is actually the B1 itself. So the B is the B1 itself, and we can check for the first property. For this element Bx, because the B is B1, so we should have X is inside the B1. This is obviously true because we choose this X from the B1, so the X should be inside the B1. So the first requirement is satisfied. For the second one, the B1, the B, because it's B1, so the B1 should be a subset of the U, which this U here is the B1. So we have this relationship. This is also true because B1 is a subset of itself. This is always true for any set. So this is true. So it means that we can use B1 as a basis element that for all the points, no matter it is X or Y inside of this B1, to satisfy those two properties. And then, because all the points can have this B1 as the basis element to satisfy these two properties, then the B1, this set B1 is open. So it's open, so it should be in the topology T. So that's why B1 is an element of T. And this is true for any basis element inside of the B. So we can verify it for any element, every element in the basis. So that's why this claim is true. And according to this claim, this sentence, it also means that because for every basis element in the basis, they are an element of the topology T. So it means that it just means that the basis B is a subset of T. So it's like this, because every element of B is an element of T. So that's what we said before. The T includes the set B. Okay, then let's look at this element now.